Yeah, thanks very much to Earthscope for inviting me to be here today. It's a great opportunity to be able to share our research. I want to acknowledge my several co-authors, which have contributed to this work: Pascal Lacroix, Andy Bell, Marin Gavorson, Simon Mudd, Menghan Huang, Adam Booth, Roland Bergman, Michael Denbina, David Beckart, and Eric Fielding. And so really this is a large collaborative effort that's been going on for a number of years, where we've been taking all sorts of different remote sensing data sets to try to better understand landslides. Okay, so the study, the presentation today is going to focus on two case studies, and really I want to just use them as examples of sort of the complex landslide behaviors that occur and how we need different remote sensing data sets to better observe them. So first, we're going to focus on the Mud Creek landslide, otherwise known as the Big Sur landslide, because it happened down here in the Big Sur coast. This landslide happened on May 20th, 2017. It had an area of about 0.23 kilometers squared. It was roughly 500 meters wide and 500 meters long before it collapsed and deposited downslope. There was no loss of life due to this event, primarily because Caltrans, who oversees California State Highway 1 here, had the foresight to close the road down. There was some indication that the slope had been accelerating, and so they shut down the road and then came back a few days later to find it looking like this. But there was an extensive repair cost, about $54 million, and this stretch of highway, which really links the northern and southern parts of Big Sur, was closed for about a year and 2 months. There's been several previous studies on Mud Creek, given it happened a number of years ago, including some work that I did during my postdoc. Here you can see an animation showing satellite InSAR from Sentinel-1. This is the velocity time series draped over a hillshade of the topography. And what it's showing is that between 2015 and 2017, the landslide was speeding up and slowing down. We can look at this in a nice static plot to better understand what was driving these changes. And so on the bottom here, I have plotted the rainfall, and we've replotted this velocity here into displacement time series. And I just want to note a few different things about the landslide. So we've broken the area into different parts. So these are complex landslides, and they exhibit these complex behaviors, and they have different zones. And so the part that actually collapsed across the road is what we call the collapsed area here. This is shown by this darker gray color, and you can see the median value of this whole zone plotted by this dark gray line here. And this lighter gray color is corresponding to this area that was moving but did not collapse. So that still remains on the slope today. And I just want to point that out because this will come back later in the talk as well when we show some more recent updates. But looking at the Sentinel-1 time series displacement data here, you can see that each year there was these increased periods of displacement that were directly driven by rainfall. And actually during this period, there was a transition from historic drought to one of the wettest years on record in 2017. And that's has been implicated as the reason that this landslide changed from a slow moving landslide and then collapsed catastrophically. There's been other studies that have also looked at the same data set, but applied different techniques. So in the study here, they looked at the InSAR coherence, which is essentially a metric of the InSAR quality. And that's what's plotted by these triangles through time. And again, here the precipitation is plotted, but now it's showing cumulative rainfall broken up into the different years. And the key thing that they found was that starting in 2017, when we saw this larger increase in displacement, the coherence also started to drop. So this was suggestive that the landslide was moving faster. This becomes problematic for InSAR, and we'll revisit some of the reasons for this later today. But these two ways to look at the same data set really are showing the same thing, that the landslide was really speeding up. And then looking back over much longer time periods, the study by Warwick et al. In 2019 looked at made a data set, a structure for motion data set using historic air photos and LiDAR, And going back to 1967, they see these hillshade maps here are, with the different colors, are showing changes normal to the original surface, with blue colors showing accumulation and red colors showing depletion. But just trying to make the point here that this landslide was moving for a really long time before it failed catastrophically. And using all these different data sets, we start to get a better picture of what was happening there. The other case study I'm going to focus on is the Palos Verdes landslides. And I wanted to show these today because this is a very interesting area that has been in the news a lot lately. If you're in the LA area or read the LA Times, you may notice every few days there's a recent article about these landslides. But these are not new landslides. However, their behavior has changed in recent years. And so this slow-moving landslide complex, so these are the, we're looking here in Palos Verdes Peninsula. We're just west of Long Beach and just southwest of downtown LA. The area has been a known slow-moving landslide since the 1950s, and they're quite large features. This is the yellow polygons are showing that what's mapped as the active landslide boundaries from the California Geologic Survey. However, this whole area where you can see people are actually living is part of a larger ancient landslide complex, and part of this has reactivated. But and we'll talk about that towards the end of the talk as well today. But going back in time and looking at all the different studies that have quantified the motion of these landslides, this is the first published study from 1960, where they show the monthly precipitation on the top versus the horizontal velocity measured by field surveys. And what they found back in 1956 through 1959 was that this landslide was moving. Its velocity was changing seasonally, again, driven by seasonal rainfall. So this is a very common and known behavior of slow landslides, especially in seasonal rainfall environments like coastal California. Back in this time period, the maximum rate was about 11 meters per year, which is a significant rate. But in more recent years, the landslide has slowed down quite a lot. So this is the first InSAR study of the Palos Verdes landslide, looking at this data set from 1995 to 2000. These were using the ERS-1 and 2 satellites. The study by Calabro et al. Found that landslide was moving at about 2 meters per year or less, so much slower than it had been back in the 50s. Some other work has used both pixel tracking of worldview images and InSAR from the Cosmos SkyMed satellites between 2007 and 2017. They actually mapped the whole slope area into these different zones, quantifying them as slow, very slow, and extremely slow landslides, where slow landslides are kind of in this meter per year or range, and you can going down to the millimeter per year range into the extremely slow. But again, finding that there's essentially this main active zone that's been persistent since the 1950s, although the rates had been decreased from the initial study that quantified its motion. And then the most recent published study on this area was led by Zheng Li. It was a postdoc that I was working with last year. And Zheng looked at the Sentinel-1 InSAR time series for the Portuguese Bend landslide and other nearby slow-moving landslides in LA. And so here you can see the displacement time series against the rainfall again, where the rainfall is shown as in a cumulative plot for each water year. And each one of these lines corresponds to a different landslide. So the magenta shows the Portuguese Bend landslide, and the other blue data here are actually from nearby Catalina Island, which has a number of slow-moving landslides on it. But focusing just on Portuguese Bend, you can see again that the seasonal rainfall was driving seasonal changes in landslide activity. And importantly, there's been these really big changes in seasonal rainfall from year to year over the past decade or so. And starting in 2023, which was a very wet year in LA, the Portuguese Bend landslide started to accelerate, and this is when our time series ended there. And so I'll provide some updates of that today. But the reason that I really wanted to talk more about Palos Verdes is, and as I mentioned, it's been in the news a lot lately, is because there's been a big change in the landslide activity starting about spring 2023. So two things have happened. First, the active landslide area has expanded. This map here is a GPS contour map that's been made by this company, Cotton Shires and Associates, who are working with the city of Rancho Palos Verdes. So this is on city land. And what they've found is that the active area has expanded. And so the area that I'm highlighting with my cursor here is essentially the growth of the landslide that's outside of sort of the more traditional boundaries that are shown by the black colors here. In addition to the expansion, it's also accelerated. And so there's been activity here at rates up to about 30 centimeters per week over the course of the last summer, and it's moving about 80 times faster than it was in October 2022. This led Gavin Newsom, the governor of California, to declare a state of emergency in September 2024, and that happened after about 250 houses that are primarily in these areas here and over here, and up in the upper slope, some of the upper slope areas lost power because the utility companies had to shut off the power because of the increased land activity. Since the summer, there's been 6 dewatering wells installed, and they're pumping about 1.5 million gallons per day. And most of these wells are kind of down in this coastal stretch in the southeastern part of the slope. And they've found that since the pumping has started, the average rate of movement has decelerated to about 8 centimeters per week. So it seems to be working and draining the water from the slide. So with that introduction, I'll just to mention what I plan to show here today is that I'm going to provide some updates for the Mud Creek landslide. And in particular, we're going to show how new measurements of surface motion from pixel tracking of LiDAR and PlanetScope optical data have revealed a part of the landslide acceleration that we had missed with the InSAR data, and that using this, we could have actually forecast the failure time days in advance. And then for Palos Verdes, I'm going to show new InSAR and coherence time series from Sentinel-1, as well as a new InSAR data set from UAVSAR, which is an airborne SAR system, and that really the combined approaches here are what we need to capture the broad range of deformation that ultimately will enable us to better understand landslide properties and behaviors. Before I jump into more of the methods and results, I thought I would just take a step back for maybe those who are less familiar with landslides or slow-moving landslides in particular. And so we can look at this nice cartoon hill slope and talk about some of the mechanisms that lead to slope failure. And so essentially, a landslide occurs when the shear stress from gravity on the slope exceeds the shear strength. There's a number of factors that can perturb the stress balance and cause a landslide. The 2 most common are from precipitation, and so this can be in the form of rainfall or snow melt. And when the liquid water infiltrates into the hill slope, it raises the groundwater table and increases the pore water pressure, which weakens the material. Also, earthquakes can perturb both shear stresses and the shear strength and lead to slope failure. There's also important considerations from human impact. Often we pump wastewater and things into slopes that may lead to failure. We build on top of them and load them in different ways. We cut the vegetation down and allow more water to infiltrate into the slope. And we do things like build roads and cut them at their toe, and even make reservoirs and change the reservoir height. And all of these things can work in different ways to change this stress balance on the slope. Looking back at a pattern I've already sort of showed through different data sets, when we monitor slow-moving landslides in particular, we often find displacement time series that look like this. So you see these sort of stair-stepped patterns through time. And these changes in displacement rate are often caused by changes in pore water pressure, and this is the result of this infiltrating rainfall, which increases the pore water pressure. You can look at this in equation form using the definition of the shear strength. If you see the pore pressure goes up, that's this P term, the strength goes down, and that causes these periods of acceleration. And so you can look at each one of these increased displacement periods and sort of assume that there may have been an external forcing that drove that change in behavior. And slow-moving landslides can exhibit these types of behaviors for really a long time. I showed for Palos Verdes, the landslide's been moving since the 1950s. So we're talking decadal scale patterns like this, and it can these slides can continue sliding slowly, for indefinitely, or eventually can stop, or they can fail catastrophically, which is the case of the Mud Creek landslide. So that's when there's been a runaway. There's a displacement essentially runs away and the whole slope collapses. For our methods, we are primarily measuring surface deformation with remote sensing data sets. That's the main thing that we can track, and then we have to make assumptions about what's going on underneath the ground to try to better understand the landslide overall. For surface deformation techniques, we're using two primary techniques. One is called pixel offset tracking. It also goes by other names such as image correlation. This is essentially tracking shifts in the pixels of remote sensing data sets from image to image. Here, for Mud Creek, I'm going to show some pixel tracking results that we did with the two different LiDAR data sets, so multi-temporal LiDAR, as well as the commercial PlanetScope optical data. You can see examples of these data sets here for the Mud Creek landslide, and as they sort of play back and forth through time, you can even see the slope clearly moving with your eyes, which means that we should be able to nicely track it with our pixel tracking computer techniques. We're using LiDAR data that was acquired by the USGS 3DEP program, but was accessed through Open Topography. And we accessed PlanetScope commercial data through the research education commercial license, which is open to all academic researchers, that you can get these nice 3-meter pixel size optical data sets with almost daily revisit time globally. The primary limits for pixel tracking is that, especially in the context of landslides, is that they're not really well suited. These techniques are not really well suited for measuring small deformations. And small here I'll label as sort of centimeter scale, even a few tens of centimeters. And that's really a factor of the pixel resolution of these input data sets. So given the most common data sets, and even in the higher resolution range, are sort of these meter to 3, low end meter scale, we can measure really confidently several tens of centimeters. If we had a higher resolution data set, we could measure smaller deformations because we're measuring sub-pixel shifts, so a fraction of a pixel. For optical data sets, there's also a big limit is cloud cover, and so cloud cover does impact the Mud Creek data set that we looked at, and so it ultimately lowers the temporal sampling of the data sets. And of course, when the ground is really heavily vegetated, for all remote sensing data sets other than LiDAR, which can penetrate vegetation, that often causes problems because we're not actually measuring the ground motion as we are measuring changes in vegetation. The other data sets that we use are satellite and airborne InSAR techniques, and we're using data from the ESA Sentinel-1 satellites, as well as the NASA-JPL UAVSAR. We also rely here on a combination of data that we've processed ourselves, as well as standardized open access interferograms that are processed by the JPL Caltech ARIA project. And InSAR works really well for measuring the smaller deformations, so things at the kind of centimeter scale to millimeter scale, but is not well suited for large deformation. So there's problems as the technical limits of InSAR, which will come into play in our reanalysis of the Mud Creek data, which show that we actually missed a large component of the deformation due to this technical limit. Also, of course, vegetation causes problems with InSAR. And in the context of landslides, we are often limited by the ability to measure the downslope motion of landslides, which may not be optimally oriented to the radar line of sight, which is how InSAR is measuring. And here you can see an example of a InSAR velocity map draped on a hillshade, showing these red or colors here are corresponding to these active landslides. I just wanted to mention, given we're at the EarthScope seminar, that EarthScope has been really fantastic resource over the years. Has supported both data and software that are useful for InSAR processing. And really, one of the biggest things that comes up in the InSAR community is the yearly InSAR trainings that are provided by the EarthScope, which have been fantastic in training the next generation of InSAR scientists. So here we also take this surface deformation data, and we've tried to do some forecasting using this failure forecast method. So the failure forecast method is a commonly used approach for trying to forecast failure of things like landslides. It's been used for a number of decades, as well as things like predicting volcanic eruptions. And the failure forecast method that we're using is specifically the one developed by Andy Bell, which is using this Bayesian Markov chain approach. But we essentially are trying to fit parameters to this equation where we can measure a geophysical precursor, such as this could be strain, displacement, or number of earthquakes. Here we're measuring displacement with the remote sensing data. And we really want to try to fit these constants, which enable us to make forecasts. And the data, these displacement through time data in the forecasting context are often plotted as this inverse velocity here. And these, they can take different shapes, but the linear inverse velocity is most commonly sort of assumed for things like landslides. And this enables you to then plot your data set and sort of project it out to the failure time. And that's where the forecast ability comes in. So I just wanted to make a special mention of the UAVSAR system that we're using, because we recently acquired special new data for the Palos Verdes landslide. So UAVSAR is the uninhabited aerial vehicle synthetic aperture radar. So it's not a drone. It's a Gulfstream 3 airplane that's crewed, and then it operates with different radars, but in our case, we use this L-band radar, which has a 24-centimeter wavelength. And really, the key advantages of using UAVSAR for landslide monitoring in particular are that one, provides high-resolution data, so we're talking sort of meter-scale pixels. This contrasts from the satellite data that I neglected to mention on the previous slide, but is a sort of a moderate resolution, 5 to 15 meter pixel size. So we're looking at a much higher resolution, which is often better for monitoring landslides that tend to be quite small. We can also design the flight paths specifically to image the slopes, where the satellite, we're limited to its set configuration. With the airplane, we can actually look at slopes and design them to properly image the landslides that we're interested in. We can also make multiple overpasses in different directions, which allows us to go one step further from measuring line of sight changes to actually solving for the true 3D motion of the slopes. For the UAVSAR data that we looked at in Big Sur, we are able to use data that was acquired between 2009 and 2016. There was 14 images acquired covering the Mud Creek landslide along one flight direction. And this was actually just a fortuitous case where this data set had been collected for all these years because it was imaging the Central San Andreas Fault for a different project. And it happened to fly all the way out to the coast, covering Mud Creek, which enabled us to use it and try to understand the longer motion period than the satellites provide, and also enabled us to solve for the 3D deformation of Mud Creek. For Palos Verdes, we actually just recently collected images between mid-September and mid-October of 2024. We were able to get 4 different images along these 3 different flight paths. And this was in direct response to the ongoing disaster there, and wanting to really get a full understanding of what's going on with that slope. So first, we'll look at some of these new updated results from Mud Creek, and I'm going to start by showing you some velocity maps. On the left, you can see the result of the LiDAR pixel tracking. This is using 2 LiDAR data sets from 2010 to 2016. On the middle, you can see the result from InSAR, which combined the UAVSAR and Sentinel-1 data sets to go from 2009 to 2017. And what you can see here is the horizontal velocity on the slope. The vectors are shown by the horizontal vectors are shown by these lighter kind of transparent arrows, and then they're plotted on top of the velocity, showing with redder colors correspond to higher velocities. Again, just wanted to reorient you with the different polygons here. So the dark black line highlights the area that was moving before the slope collapsed, and this dashed black line shows the area that ultimately collapsed across the road, which is shown here, and also includes its deposit. But looking at that, we wanted to compare, given these are similar time periods, but 2 different techniques, we wanted to compare the results to see if they agreed. And so just to make it a little bit easier to make a one-to-one comparison, we extracted profiles. And in the lower right corner, you can see there's a downslope profile that goes sort of down this western lobe, and that's this plot on the left. And there's a cross slope profile that goes across here that you can see on this right plot. And the InSAR is shown in the orange color, and the LiDAR is shown in sort of this reddish color. And what you can see is that there's at least a good agreement in both the shape and the overall magnitude of motion. The landslide was moving during this time period at rates of about a half meter per year or less. And it sort of was moving fastest in the upper slope region and decreased down towards the road. And then you see also there's these 2 sort of lobes that are separated by the Mud Creek Channel, and those are nicely captured in both data sets. We then compared this to the pixel tracking results from the PlanetScope data. So these were looking just at data from August 2016 to May 2017. And we found a much different result. So we see that first, the magnitude of motion is much higher than was revealed by these other data sets, which suggests something had changed within the slope, which we know because it did collapse. However, we now are able to actually measure this change. And so we're seeing rates up to 15 meters per year or so during this full time period. And importantly, we also see that the fastest moving area actually localized within the zone that ultimately collapsed. And you can see that by looking at this downslope profile too. You see the highest rates are actually occurring in the lower end of the slope. We also were able to extract the time-dependent motion from the PlanetScope data. So again, this is a plot I showed in the introduction. This is the InSAR time series, and these data were published in our previous work, although we've sort of replotted them by breaking them into these different zones again. But the key thing was that one of the conclusions of our former work was that we were not able to essentially forecast when the slope was going to fail. We know that in 2017, it was moving faster than it had previously, but there was no clear sign that it was going to accelerate and collapse. But this differs when you look at the pixel offset tracking result. So here we're now looking at displacement in meters, going up to 12 meters, where here we were less than a meter over this full 800 days. We've zoomed into just the last about 300 days before failure. And the yellow colors are showing this area that collapsed. The blue colors are showing the area that was moving but did not collapse. And you can see distinct behaviors occur starting about 100 days before failure. You see that the area that collapsed increased, it's just moved significantly, about a couple meters, before slowing back down temporarily and then exhibiting this runaway pattern that's sort of characteristic runaway behavior. Whereas the area that did not collapse sort of stabilized and was just, it's still moving and still moving to this day, but did not collapse. And notably, these magnitudes are just much different than the InSAR data. So this shows the InSAR data missed this whole period of motion. And you can see, actually, I've plotted the InSAR data on the same scale, and it essentially looks like a flat line. So all of this, and these changes in behavior, again, were driven by rainfall, right? So the rainfall period is going on here, and you can see that at about this time, after several months of rainfall, the landslide starts to accelerate significantly. And then also of note is that even though the rainfall essentially stopped in late March, the landslide continued to accelerate even without any further input and then collapsed on May 20th. In addition to the timing of motion, we can look at how the spatial evolution and the strain rate change. And I found this to be a very nice way to sort of see how the strain localized in what ultimately became the catastrophic failure. So these are just 4 time snaps of the dilatation. So where red colors correspond to extensional motion and blue colors correspond to compressional motion, and also the maximum shear rate. And what these show is that starting about 30 days before the failure or a month before failure, you start to see strain localizing in the area that became the catastrophic failure. And by about 6 days before, you can really nicely see the outline of this part of the slope that failed. So this suggests that these PlanetScope data would have provided information on the timing of motion as well as the spatial area that had changed. And then, as I mentioned, we went a step further and provided this, looked at this failure forecasting approach that was developed by Andy Bell, where first we do a retrospective analysis. So the plot on the right is showing the displacement time series, and these black lines show different model fits based on this whole simulation. And the retrospective analysis just means that, you know, we know it failed on May 20th, so we already can fix some of these parameters, and we want to try to figure out what the exponents were. And what we found is that it leads to this exponent of a value of 1, which is consistent with that linear inverse velocity pattern and is a hyperbolic trend. This is all. There's been other studies that have suggested that this type of failure is indicative of crack growth rather than crack nucleation. And so we found, you know, when we know when the failure occurred, we see good results, but we could also simulate as if we were collecting data in real time when we don't know when the failure is. And so we can do this by essentially dropping data and going and then adding it back in as if it were coming in real time. So starting about 70 days before the failure, you can see you actually would have had the model would have predicted a failure that did not occur, and that's due to this little increase that we first observed. This kind of increase before it's slowed back down and then increased again. But if you keep monitoring and keep adding in data, you start to find the true answer as you get closer and closer, and you can look at this in a probability form. So this plot shows the failure forecast time in days on the y-axis versus the days before failure. And then the colors correspond to a higher probability. So essentially, what we want to do is be able to hit this white horizontal line, which is the true failure time, as far to the left part of this plot as we can. And to make it a little bit easier to see how these results translate into this, we've taken 3 time slices shown by the blue, green, and red lines here. Then this is them plotted again as the probability of that failure at these different times. And what you see is that as you get closer in time and have more information, you start to converge on the true failure time. And here we find, and so the red probability is really highlighting the true failure time. That happened about 6 days prior to failure. So at least by 6 days before failure, we would have had the forecast right about when the landslide was going to collapse. I'm just going to end here by going through some of these new results for Palos Verdes, and then trying to tie it all back together with how we're learning about these landslides with different data sets. So as I mentioned, there's been a number of studies on Palos Verdes landslides. I've showed some of the Sentinel-1 results before. This is a new Sentinel-1 time series using the same input data, but here I relied on these standardized interferograms produced by the ARIA project. On the left, you can see the displacement map. And these different polygons are showing different things. So the dark black lines show what have been mapped by the California Geological Survey as the active landslide boundaries. And these dashed black lines show part of this ancient landslide complex that has not been thought to be currently moving. However, that's what changed in June 2023. And so June 2023 is about when the first reports of really high deformation rates started to happen. And so we know the InSAR data become unreliable at that point. And so we truncated the time series. So on the right, you can see the orange lines again showing displacement and the blue lines showing cumulative precipitation. We see there are these seasonal changes in displacement driven by these seasonal changes in precipitation, and that these large year-to-year swings in rainfall are driving the changes in landslide motion. I've just extracted 3 points here, 1, 2, and 3, going from top to bottom, 2 of which are within the Portuguese Bend landslide, and 1 is in this landslide called Abalone Cove, which is part of the larger complex, but is a distinct landslide. And you can actually see distinct behaviors, particularly starting in 2023, where the Portuguese Bend landslide starts to increase its displacement rate significantly, whereas the Abalone Cove continues to slide at its more sort of constant rate. And all of these really started increasing in their rates back in 2019, which is one of the really wet years in LA. But we know we have this challenge with InSAR, satellite InSAR, that we can't observe high displacement rates. And so we can try other techniques to even using satellite data. And so I mentioned before that I showed the results from Mud Creek of this coherence approach, which is the coherence again is a metric of the InSAR quality. And one of the reasons that coherence can decrease is because of things of fast ground deformation. And here was our attempt to try to understand if this was a usable technique for Palos Verdes. And so there's a lot on this plot, so let me try to break it down in detail. We can start with the top row here. So what I've done is I've taken the 12-day coherence. So 12 days is about the normal repeat time for the Sentinel-1 satellites that cover the same patch of ground every 12 days. And then I've binned them by month to make this calendar of coherence. The top plot shows the average between 2017 and 2022. And so this was an attempt to make what we could consider the baseline, or what the coherence should have looked like under normal conditions before this large acceleration occurred. Again, we've plotted, in addition to the coherence, so red colors here correspond to low coherence, which might be indicative of faster motion. On top of the coherence plots, we've added the landslide polygons as well as buildings. That's what you can see by these white polygons here, and roads as well. And looking at this very top row first, you can see that normally, LA is a relatively dry area and there's relatively light vegetation on this slope. And so normally the coherence is actually quite high year round in Palos Verdes, except for the few rainy months where the landslide does move a bit faster than normal, and also at the time that it's raining. But if you look at the 2023 and 2024 water years and compare that to the top row, you can see there the coherence starts to decrease as the rainy season starts in 2023, and it really never recovers, meaning that the coherence stays low through the rest of this time period. It's particularly noteworthy if you look in the summer, which is really the dry season of California. If you look at August, for instance, and just scan up and down the column, you can see here that the coherence is staying low, even in the absence of rainfall, when we know the landslide was moving fast. So coherence doesn't tell us how fast the slide is moving, but it does provide some information about what part of the slope is moving, and also how that can change over time. So you can see there's different, as you progress forward, there's different areas that were showing low coherence, which suggests that different parts of the slope were moving. Then we have the newest and latest data from the area is from this UAVSAR data set we collected, and we collected these, as I mentioned, on 3 different flight paths. This is just one of the flight paths where the line of sight is looking directly up the slope. And what we found in these 3 interferograms, which go from about 12 days to 8-day range, that there's this huge area that's outside the mapped active zone that's moving, and the slope's moving at the centimeter per week sort of scale. But we can take the 3 overlapping flights and invert for the 3D velocity, and that's what we're showing here. So now I've plotted again the horizontal velocity vectors, as well as the 3D magnitude of velocity, showing sort of a maximum of about 10 centimeters per week. And we see there's a really good result. This agrees well with the other data sets that have been provided. And just to convince you of that, we can plot 3 different data sets side by side. On the left, you can see again this GPS-based contour plot from the field collection going on by the city of Rancho Palos Verdes. We can compare that to the UAVSAR and also to the most recent coherence map from October. And you can see they all nicely capture the same spatial extent, and the magnitude of motion is measured well by the UAVSAR data and agrees well with the GPS measurements that we see here. If you're interested in these data, I just want to mention that as part of our work at JPL, we've been working with the NASA Disasters Program to provide these data sets to the California Geological Survey and any other stakeholders as part of the emergency response. They're available through the link you can see here. If there's not time to jot it all down, just go to the NASA Disaster Portal and you'll be able to actually download and visualize these data sets. And okay, so covered a lot here. So do a quick summary, and then I'm going to end on one final future directions thought. So to summarize, we showed that the Mud Creek and Palos Verdes landslides exhibited these long periods of slow motion before accelerating. And this really challenges the different data sets that we need to use to capture these behaviors. We know that the increased rainfall is the primary driver of these behavioral changes. We found that satellite InSAR is really best suited for monitoring slower motion, while pixel tracking techniques are better suited for monitoring faster motion. UAVSAR is great because of its flexible ability to collect in image slopes. We can capture both slow and fast motion. Here we showed an example where we used short interval interferograms to capture the fast motion that the satellite data can't collect. We found that failure forecast methods can work well, and that the PlanetScope data provide a great tool with high revisit time that may be useful in landslide forecasting. But really, that just the main takeaway is that these multi-sensor remote sensing approaches, of course, with ground measurements to both validate and verify the measurements, captures the broad range of deformation that can reveal landslide properties. Now, the last point I wanted to draw your attention to here is that at JPL, we're leading a project called OPERA, the Observational Products for End Users from Remote Sensing Analysis. And one of the things that OPERA is making, we are making a North America InSAR displacement time series product. On the right, you can see the geographic coverage that OPERA will be creating the InSAR displacement from. So it's not just the US, but it includes parts of Canada as well as Central America and all US territories. We'll be making these data sets from Sentinel-1 going back to 2016, and also from NISAR once it's launched. And the first release of the displacement product will be actually next month. So it's very, very soon and relevant. And if you have more interest in learning about OPERA, I encourage you to see our website here. And just to show you a sneak peek of what you can expect from OPERA, this is the OPERA Sentinel-1 displacement data set from the Palos Verdes landslides. And again, we've seen this now a variety of different ways from the same data set, but just to show you, you'll be able to just go and download these data. They'll be ready to use rather than having to go through all of the pre-processing steps that I went through to create the data sets here. And with that, I am done and am happy to take questions. So thank you very much.
Thank you so much, Al. That was fascinating. It takes me back to my days of being more of a geomorphologist. We have several questions that have come into the Q&A. I did want to note that someone had raised their hand as well, but we don't have the way to unmute. So please ask your question in the Q&A window. So from the first person so people can give their name or be anonymous in the Q&A. So it was an anonymous input. How did you choose a reference point? Which parameters did you consider because it's outside of the area of interest?
So I Yeah, so something I didn't explicitly mention, so thank you for asking. InSAR is a relative measurement, which means that we always have to define a 0 reference point. And so we do that. I primarily do that by looking for a location which I have to assume is stable. And so for the case of Mud Creek, I looked at a nearby area where there were some houses, and I picked those houses, the roofs of those houses, as the stable point. And I had plotted a stable, and then to make sure that we weren't seeing any motion in other areas, I also so everything is relative to that point. And then I also looked at an area that was not that point that I also thought was stable, and I had plotted that on those plots to show essentially zero, hopefully zero displacement, although I did neglect to call them out when I moved past that. But I mostly do this using just sort of like information about what I think is moving, as well as Google Earth and tools like that that can really help you zoom in and look at an area.
Awesome, thanks. Next question from Susan Schwartz. Why didn't you analyze PlanetScope data for the Palos Verdes landslide? Is the motion too slow?
Thanks, Susan. No, it's not too slow. All of that work has been done in a very short amount of time in the last few months. And so there's definitely, I mean, I'm quite confident the PlanetScope data will be very valuable for monitoring the fast motion there. I just haven't been able to do that yet. I have seen colleagues in France, in particular, Florian Provost has shown me some results from Sentinel-2, which is a coarser resolution optical data set with a 10-meter pixel, and she was able to track the motion of the landslide from pixel tracking very, very well for the last year. So definitely a worthwhile thing to do. Yeah.
Thank you. Another anonymous input. Which polarization did you consider in UAVSAR L-band data?
So for the displacement data sets that we've derived from UAVSAR, we're always using the horizontal transmit, horizontal receive polarization. In most cases, it does the question is probably and thinking about UAVs now, some knowledge of UAVSAR. So UAVSAR does collect data in 4 polarizations. So there's a choice. I've always just used the horizontal polarization and have not explored other ones.
Thank you. Earthquakes, co-seismic motion would be slow or fast to capture, slow or fast. To capture it, is it better to use the optical images then? I think maybe what they're asking.
Yeah, let me see. I'll try to answer. So I don't know, do you think the question is related to earthquake-induced motion on landslides or for earthquakes in general? Earthquake deformation.
Actually, maybe I'll say to the anonymous person that put that one in, if you can add a clarifying version of that, and we'll go on to another question in the meantime and try to come back to it. So from Taraka Patela, are there other monitoring systems? If yes, did you compare your remote sensing results?
So in the cases I showed, so Mud Creek had no other monitoring system on the slope, so there was nothing to compare it to. As I showed for Palos Verdes, there are GPS. So there's a company working with the city of Rancho Palos Verdes that are doing regular repeat surveys of the GPS data, and we have not been able to actually extract those data to do a one-to-one comparison. But I showed, my best attempts for today was to look at just sort of a visual comparison, and we're finding really especially the UAVSAR to GPS comparison is showing same order of magnitude and same spatial extent that is being mapped as active by the field surveys. but that needs to be done. An actual, one-to-one GPS to InSAR comparison will be great. And those data are provided by the city. They're on a website. They're just in a form that I haven't been able to easily extract yet, but it's definitely possible to do that.
Okay, cool. And I guess, of course, there's also the like houses are moving and things like that sort of on the ground information. Okay, a question from Renzo. Which software is better, GMT-SAR or Snap for doing InSAR processing?
I don't have any specific knowledge to that question. In fact, I've never used GMT-SAR, so I don't know about it. My understanding is that the publicly available InSAR softwares such as Snap, GMT-SAR, and ICE, which is what we use at JPL primarily, they're all fantastic, and I don't think that one is better than the other. And in my experience, people who use one or the other are primarily because they use the one they learned to use first and stick with it. But that's just my personal experience. But yeah, I would imagine they're both great, and I wouldn't be worried about using one over the other.
So the one that someone can learn, essentially.
Yeah.
All right, from Nick, your future direction slide shows coverage over the US and Mexico, but not Canada. Is this what the Opera website is calling a North America displacement product suite? What would it take to get Canada included in North America?
Yeah, that is correct, Nick. So the extent we're doing is a little bit funny in the context of the word North America, and really there's usually I write an asterisk next to it to try to signify that it's not all of North America. So our scope is Opera is really a project that's supported by the U.S. federal agencies, and so that's the primary focus. So we cover all of the U.S. In U.S. territories, and then we were able to expand through Central America all the way down, through Panama, and then 200 kilometers into Canada over the northern border, as well as the entire Cascadia subduction zone, which isn't quite visualized correctly on this image on the right, but we are covering the full Cascadia subduction zone all the way up through, up into essentially on the west coast of Canada, all the way through Alaska. And the primary reason is really a financial one. It's not a capability. And so we were able to cover, the main population centers of Canada, but because this is supported by U.S. federal agency project, and there's not sufficient funding to go all the way through Canada. So really, it's just a matter of funding. The algorithms and approach will all be the same, and so it is a possibility in the future.
Awesome. It seems like there's other interest in Opera, so I think people will be going to that website. I think we have time for one last question. So we'll say, how is the velocity averaged over the entire slope to create a single velocity plot for a slope with many complex displacement rates?
Yeah, that's a great question, and that is always something that I struggle with, because the whole point is that these are complex slopes and they can somewhat exhibit somewhat distinct behaviors even within a slope. And so I showed a variety of things today. One version of the plot I did I took those two different polygons and I plotted the median value within that polygon. Or I pick a point which is different from another point. And really it requires someone to explore around and look at the different data sets. You'll see in some of the plots, especially for Mud Creek, I actually plotted the full range of values in this background shaded area. And I think that's a nice way that you should utilize every pixel and try to see if there are distinct behaviors within the landslide. But to make like a summary, I made a decision about showing what I thought was the representative value or pattern of that part of the slope, and so that's how it was chosen. But it's definitely worth being careful and thinking about.